Okay, thank you. Okay, so yesterday we have looked into the Brayton cycle, the gas power cycle. And just to recap a bit on the gas power cycle, let us sketch what we have learned yesterday.
Sir, yesterday sir want to discuss about the cylinder, sir. Something
Yeah,
about the
okay.
cylinder.
Cylinder, no, is it a cylinder? Cylinder or combustion chamber?
Combustion chamber, sir.
Cylinder.
DC, sir.
Not cylinder, combustion chamber. Wait, guys, I cannot open my whiteboard. Thing wrong. Let me close it again and reopen it. Something wrong. Hmm. Yeah, and guys, I'm waiting my whiteboard to be connected online. Oh, tadi tak ada masalah pun, ada masalah pula. Okay lah. Ada problem sikit. So while waiting for the whiteboard to respond, so let us look a bit on the textbook and what we have learned yesterday. Okay, so yesterday we have looked at the Brayton cycle. So this Brayton cycle is the open type of a Brayton cycle, whereby we can see that there is no closed loop. Okay, there is no heat exchanger at this part. Okay, so we don't need to condense or we don't need to cool off the exhaust gas. We know that the exhaust gas is going to be emitted to the surrounding, then what is going back into the plant is a new fresh charge of air. And then in the combustion chamber, we are going to inject the fuel, and we are assuming that the m dot of the fuel is much less than the m dot of air intake. Then what we do is we neglect the mass of flow rate, the mass flow rate of the fuel. So it becoming 0. Then we have the turbine, the expansion process, and the turbine will produce our positive work. And we know that this plant is a self-sustained, meaning that the turbine will run the compressor, or the work part of the work from the turbine is going to run the compressor. Then what we have, the rest is the W net, whereby the W net is equal to the W turbine, W34 minus our W for the compressor, which is 1, 2. So as far as the W net is concerned, that is how we get W net. And then if you want to evaluate the performance of this plant, then we need to know what is the Q being input to the combustion chamber, which is referred as the Q23. And for the compressor work, W12 is equal to CPA T2 minus T1. And then for the Q23 is CPG T3 minus T2. And then for the turbine, W34 is equal to CPG T3 minus T4. And for this state 1, usually referring to the ambient condition, P ambient, T ambient. And then this T2 we get from the compression process of isentropic or reversible adiabatic compression. And then the T3 usually is given and it depends on the type of fuel we use. And then the T4 is basically based on the expansion process. And in this case, we are assuming that the expansion process is as an isentropic expansion. So S3 equal to S4. So that is how we look in terms of the SFEE and how to evaluate for this case. And then as for the TS diagram is concerned, 1, 2S is the isentropic compression, and then 1, 2 is the actual compression, taking care of the isentropic efficiency. And then 3 to 4S, this is the isentropic expansion. 3 to 4 is the actual expansion, basically based on the isentropic efficiency. Yesterday, we have looked how we solve for T2, T1, T3, and T4S. Now, to look into the T2 and the T4, we are going to use the definition of isentropic for the compressor, which is equal to isentropic compression, which is CPA T2S minus T1 divided by CPA T2 minus T1, right? And assuming that the CPA is the same as a constant, what is left is the T2S minus T1 divided by T2 minus T1. From this equation, we are solving for the T2. Okay, we are solving for the T2. And then as for the isentropic efficiency for the turbine, which is the definition is the actual work produced by the turbine, which is CPG T3 minus T4 divided by the CPG T3 minus T4S. Okay, and this from this particular equation, we are going to solve for T4. Right, so this is not an ideal Brayton cycle, whereby we are looking at the losses, okay, and the losses of the compression and also the expansion process. So as far as the W net is concerned, the W net is W34 minus W12. And if you can look carefully, the starting of heat supply will begin from 2, not from 2S. Okay, it's from 2. That's why we can see that the highlighted line is from 2 to 3. This is actually what we are going to put in the combustion chamber, which is the Q supply, 2 to 3. Okay, so be careful of this 2S and 2, right? Let me see what happened to this whiteboard. Can I have the access already or not? Oh, still can't access the whiteboard. So how am I going to write anything? Alamak, si mana ni? I used to use whiteboard Kalau yang lain tak berapa seronok pula. Okay. So this is all the SFEE for the work input, the heat supply, the thermal efficiency. Okay. And then as for the thermal efficiency of the Q in right here, the Q in is always using CPG. Okay, using CPG. This is where we neglect the mass of fuel because the mass of fuel is much less or small compared to the mass of air. So this is the isentropic efficiency of the compressor. We assuming Cp is constant, and this is the isentropic of the turbine. Okay, assuming Cp of the gas is equal to what we have right here is T3 minus T4 divided by T3 minus T2. Still cannot access. Any idea, guys? How can I accept of rebooting my computer lah? Tak boleh juga Alright, so I need to use other type of
So maybe can use the close the unused app. Maybe that would help.
close the unused tab.
Unused app like I don't know, maybe the
I'm going to use the, or you want me to close everything and reopen it again?
maybe like the photos, the Mozilla Firefox.
Firefox, I need it because I'm running the WebEx.
Okay, okay. Yeah, I think.
Let me see. I think I have to reboot it because I need the whiteboard. Still can't access, you see? It cannot be highlighted. Okay, guys, I'm going to reboot my computer. Okay? So give me 5 minutes. Thank you.
All right, Doctor.
Okay, guys, I still can't access my whiteboard, so I'm going to use this pen. Can you all hear me?
Yes, sir.
Yes.
Okay, thank you.
And Doctor.
Right. So let's go back to the textbook. Okay, so we have looked at this. Then we have looked at the efficiency. Right. Let's look at this example. A gas turbine unit has a pressure ratio of 10/1 and maximum cycle temperature of 700. The isentropic efficiency of the compressor and turbine are 0.82 and 0.85 respectively. Calculate the power output of an electric generator geared to the turbine when the air enters the compressor at 15 degrees C and rate of 15 kilogram per second. Take the CP 1.005 and gamma, okay, in this case we are using gamma, okay, 1.4, and then for the exhaust gas, the CP is 1.15 and the gamma is 1.333. Okay, for a gas turbine cycle, the first thing that we need to sketch or we need to ask ourselves is to look the component involved. Okay, all the component involved. And when we see this question, we have a gas turbine unit, and then we have the pressure ratio of 10/1, the maximum cycle temperature of 700. And given the isentropic efficiencies of compressor and turbine, meaning that this is not an ideal cycle, whereby we have losses during the compression and expansion process. And in this case, we could see that we are going to use only one turbine, one compressor, and one combustion chamber. Although in this case, it's not mentioned about the combustion chamber, but the parameter of temperature, which is called as the maximum cycle temperature, is 700, usually referring the temperature outlet of the combustion chamber. Only at the combustion chamber we will increase the temperature up to 700 degrees C. So this particular plant is going to run a electrical generator, okay, an electrical generator. So if we sketch the schematic diagram, we must make sure that when we sketch it, it will represent the question. Okay, so in this case, I'm not going to look into the detail of the solution, but I'm only looking at the schematic diagram and TS diagram, right? So meaning that now what we have one turbine, one compressor, and one electric generator, right? Then the coupling should be in one shaft. We have one shaft connected to all three rotating or rotary type of the devices, which is the compressor, the turbine, and the generator. The only device that going to produce a positive work is the turbine. Therefore, this turbine will be used to run the compressor and also the electrical generator. So we have to connect the shaft in between these three devices. And a combustion chamber is the only place, as I mentioned just now, is the only place how we can increase the temperature of our thermodynamic system. So we are getting the air from the ambient, right? State 1, compress it to state 2, and please be reminded that we have isentropic efficiency, therefore this is 2 actual. And then going to the combustion chamber, we are going to introduce the mass flow rate of fuel, and we neglect the mass flow rate of fuel equal to 0. Then coming out from the combustion chamber as the exhaust gas or the combustion gases at the temperature of 700 degrees C. Then we are going to expand in turbine, then exhaust at state 4, where the state 4 is our ambient pressure, but the temperature is not the ambient temperature, but the temperature is the exhaust gas temperature from the turbine. And when we sketch on the TS diagram, this is our profile of pressure. The highest pressure, this is the smallest pressure, low pressure, and our overall pressure ratio, in this case, is P2 divided by P1, which is equal to P3 divided by P4. Then that is equal to 10/1. Okay, this is the overall pressure ratio. The maximum pressure divided by the minimum pressure, whereby the minimum pressure in this case is not given, right? No, it's not given. It's not given. Okay? So this is how we sketch the TS diagram. So from the schematic diagram, we convert to TS diagram and make sure that we are putting the right compression process, which is we have the 1 to 2S and 1 to 2 because of the isentropic efficiency. And the beginning of heat supply is from 2, not from 2S, but from 2 to 3. And the exhaust gas is at the point or the state of 4. Okay? So T1 is given, overall pressure ratio is given, then we can use the T2 is equal to T1 divided multiplied by P2 over P1 in order to get the T2S. Okay, T2S. So let us look at the compression process. Where is my cursor? Come on. Where is my, this is my cursor. Oh, I can see it. So this is our pressure ratio. Where is the undo? I can't see the undo. Where is the undo? Oh yeah, this is undo. Okay. Our pressure profile, the compression process, isentropic compression. So this is 1, this is 2, this is 2S, this is 2, and then we have the beginning of the heat supply, and then we have the expansion process, which is 3, 4S, and 4. So given right here, what is P2 over P1? P2 over P1 is given as the 10/1. The maximum temperature is 700 plus 273. So this is in Kelvin. Where is my drawing is now? Alamak. Oh, yeah, here. Okay. So basically the T1 is given as the ambient condition. Then we need to get what is T2S. So the T2S is equal to T1 P2 over P1, the overall pressure ratio. This is gamma minus 1 over gamma. Okay, in this textbook is using gamma. Okay, and this should be the gamma for the air A. And then after that, we are going to use the equation of isentropic efficiency for the compressor, which is equal to the T2S minus T1 divided by T2 minus T1. And from here, we will solve for the T2. And then the T3 is given. And then, of course, we are going to take care of the T2S. What is T for S? Sorry. What is T for S? T for S is equal to T3 P over P. This is gamma minus 1 over gamma. And this gamma involved for the turbine is the gamma for gas. And this is also for gas. And we look, this is P4. So this is P4 over P3. And then again, we are going to use the definition of isentropic for the turbine, which is equal to the actual T3 minus T4 divided by T3 minus T4S. And from here, we are going to solve for T4. So now we have solved all the temperatures. Okay, then we can get what is the W net. The W net is equal to the W34 minus W12. Okay, 12. And in this case, we are given the mass flow rate as 15 kilogram per second. Then if you want to know what is the power output of the turbine or the plant, okay, then we use this formula. The power output of the turbine, which is W dot net, this is equal to M dot multiplied by the W net. And as for the thermal efficiency, how do I scroll to downward? Kat maximum ni. Zoom view, zoom out. Oh, what happened? Okay. And then if you want to find what is our thermal efficiency, for the thermal, so for the thermal efficiency, this is equal to the W net divided by the Q in. The Q in is equal to Q23, and the work ratio is equal to the W net divided by the W gross. In this case, our W gross is a W34, which is the turbine work. Okay. So this everything has been solved. So please try it out. Okay. Please remember, any calculation, we must begin with equation. So this type of plant is giving us about 1 megawatt of power. Okay, any question? Okay, if no question, yesterday we have looked into this type of, not this type, right? Yesterday, basically, we have looked into the usage of multi-stage expansion. So if you can look for a multi-stage expansion, how do I make this clear? Lama. Sorry lah guys, I'm used to whiteboard, but I don't know what happened to this whiteboard, because this whiteboard is actually online resources. So kalau ada masalah internet, couldn't connect, so I couldn't use this software. See, I cannot scroll. I can't even scroll it. Okay. File, new, don't save. Okay. So yesterday I have we have looked in terms of the multi-stage expansion process. And if we can look at the schematic diagram of this multi-stage expansion plan, we have what being called as the two-stage of expansion and the usage of two turbine. This actually is to ease of the design of the turbine. We can use a smaller turbine in order to have a same power output as one big turbine. So this is what we have looked yesterday. Assuming there is no reheat, so this combustion chamber going here, and after that is going straight to the second turbine. So this is a turbine high pressure. So this is a turbine for low pressure. And this is our W net, assuming that it's running an electrical generator. Okay, this is our interest. And this part usually we refer as our W net. Right? And then this is our compressor, the air inlet, exit into a combustion chamber, and then going into the turbine high pressure, and then after that straight away in turbine low pressure. As far as the TS diagram is concerned, it will look like this. So this is our pressure line, intermediate pressure. So this is our compression process at the compressor side. Let's say we have isentropic efficiency. Now it's going up in the combustion chamber and going to be expand the first turbine because of isentropic efficiency. Then we are going the second expansion process of the second turbine, which is turbine low pressure. If we put all the numbering system, this is 1, this is 2S, this is 2, this is 3, this is 4, S, this is 4, this is 5, S, this is 5. Okay, this schematic diagram will give us the TS diagram as what I have sketched. And then in the textbook, we have one schematic diagram which the turbine, the work for the turbine is being separated. What we have is the what being called as the power turbine. Okay, power turbine. In this type of schematic diagram, we could have the W net as this equation, where the W net is equal to, let's say this is a point, let us give the numbering. This is 1, this is 2, this is 3, this is 4, and the exhaust is 5. Okay, 1, 2, 3, 4, 5. And for the W net, we can obtain from this equation, which is the W for the first turbine, which is W34, plus W for the second turbine, which is 45, minus W the compressor of the compressor, W2, 1, 2. So this is the equation how we get the W net. Okay, W net. And we have another arrangement whereby the usage of what being called as the power turbine. Okay, power turbine. Meaning that we are going to separate this power turbine, which is the low pressure turbine. We will use only to run the electrical generator which produce the W net. And then while the high pressure turbine will be used to run the compressor only. So in this type of schematic diagram, it would look like this. Compressor, first shaft, this is turbine, high pressure, this is turbine, low pressure. And we know that the turbine low pressure is running the electrical generator, while the first turbine is running the compressor. Give the same name, high pressure, turbine, low pressure. Of course, we need the energy input as in the combustion chamber. And then after that, coming up from the turbine high pressure, we are going to, sorry, not that part. Okay, this side. Coming up from this turbine, straight into the second turbine. Then this is exhaust. Okay. So assuming this is state 1, this is state 2, this is state 3, this is state 4, and this is state 5. Assuming there is isentropic efficiency for compressor, turbine high pressure, and turbine low pressure, then when we sketch the TS diagram, highest pressure, lowest pressure, intermediate pressure. Compression process, Q supplied, expansion in the turbine high pressure, expansion in the turbine low pressure. 1, 2S, 2, 3, 4S, 4, 5S, 5. Can you see any difference between this TS diagram and the first TS diagram? Compare these two. Can you see any difference?
No, doctor.
There's no difference. Okay, there's no difference. And then if we look at the schematic diagram, obviously it's different arrangement. Okay, different arrangement. And if we look at this generator, which I put right here as the W net, so this is our interest. This is our W, W net. Now in this case, we know that the turbine low pressure, the function is totally 100% just running the electrical generator, which we refer as the W net. And the first turbine high pressure is purposely, the objective is just to run the compressor. So what is the difference between this and this? Between this first schematic diagram and this second schematic diagram, where we separate the turbine high pressure work output is just to run the compressor, and the turbine low pressure is just to run the W net or the electrical generator. Right. So as for the relationship between the work transfer or the work, what we can write for this second schematic diagram is this equation. We have the work 1, 2, this will be equal to work 3, 4. And for this side of the turbine, power turbine, we could write here W 4, 5 equal to W net. You see the difference between the first schematic diagram and the second schematic diagram? We could separate the equation of work. Okay, we could separate the equation of work. But if you want to use the first law of thermodynamics for the second schematic diagram, you can do it, no problem, whereby you can define the W net of this second schematic diagram is equal to the W 3, 4 plus the W 4, 5, okay, minus the W 1, 2. And we can see that the W 1, 2 is equal to W 3, 4. This is minus, meaning that these two parameters can be cancelled off. Then what we have right here is W net equal to W 4, 5. Can you see this? Huh? W net is equal to W 4, 5. And from here, we can see W12 equal to W34. If you want to use this equation, also no problem. Because this is the, what we call that, this is the equation of summation of work, which will lead us to the W net. So this is the equation that we use. Sigma W is equal to the W net. So these are the extra equation that we can use for this type of arrangement. Whereby, for the first arrangement, we only can use this equation. The first arrangement, you cannot say that W turbine high pressure equal to W compressor. No. You cannot say that the W turbine low pressure equal to W net. No. You cannot do that. Okay, because we have attached all the components in one shaft. But for the case of separating the power turbine, which is this one, then we can separate. We can say that W45 is equal to W net and W12 is equal to W34 because there is no attachment of shaft in between this turbine and also this turbine. So that's why it's been called as the power turbine. Another one is for the compressor turbine. And this relationship will give us or will lead us to the temperature one of these 1, 2, 3, 4 temperature. Also for this case, it might lead for us to get what is the power or the W net produced by this turbine low pressure. Okay? And another thing that we need to know is the what being said as the mechanical efficiency. Remember, we learned about efficiency. What is efficiency? The efficiency is basically being defined as the efficiency. This is for mechanical efficiency. Let me put the general term of efficiency. Efficiency basically is equal to the desired output divided by the required input. Okay? And usually, in our case, we are going to look in terms of work and work ratio. Okay, work and work ratio. If we compare the thermal efficiency, the thermal efficiency is depend on the work output divided by the heat input. That is thermal efficiency. But if we look in terms of the mechanical efficiency, usually we refer as work divided by work. And in this case, if work divided by work, usually we are going to refer as the mechanical efficiency. So in this case, from turbine high pressure running the compressor, if there is losses, then the losses we are going to put in terms of this mechanical efficiency. And again, here also we are going to put the mechanical efficiency. We compare the W net and the W turbine low pressure. So if we look in terms of the definition from compressor to the turbine high pressure, and we apply this definition of desired output divided by required input. So what is our mechanical efficiency for the compressor and the high pressure turbine? Which one is the desired output in this case? Which is our desired output? Compare this turbine high pressure and compressor. Which is our desired output?
W34, sir.
1, 2.
1, 2 or 3, 4? Which one?
1, 2. 1, 2, sir.
1, 2. Because that is the required work to run the compressor. Correct? So that should be our output. Who give the work? The turbine is giving the work. Meaning that the required input is from the turbine side. So in this case, if we look at the mechanical efficiency from the compressor to the turbine high pressure, we know that the turbine high pressure is running the compressor. So meaning that the losses will be while transmitting the work from turbine high pressure to the compressor. Okay? And if we have mechanical losses, then what is being received by the compressor is less compared to the work produced by the turbine high pressure. So if we look in terms of the definition of efficiency, now we are going to have W12 divided by W34. While for the turbine high pressure to the electrical generator, which is our W net, then if we apply the same definition, what do we have? As far as mechanical efficiency is concerned. For the turbine low pressure shaft to the W net, which one is our desired output?
W net.
Yes, W net. This is our W net. And our required input is the work produced by our turbine low pressure. Okay, so this is W45. So this is the case whereby we have losses during transmission of work. We know that the work produced in this plant is the turbine, both turbine in this case. So while transmitting the work, we have some losses, maybe because of friction, maybe because of the usage of geared system, and etc. Okay, so this is the definition of our mechanical efficiency. Question?
No, sir.
If no question, let's see if I can. Saya tak boleh lagi Right. Let us look at one question from the textbook. Okay, before that, I'm trying to sketch this example, the schematic diagram. So let us look at the schematic diagram of this example. A gas turbine unit takes in air at 17 degrees C and 1.01 bar. And the pressure ratio is 8/1. The compressor is driven by the high pressure turbine, and the low pressure turbine drives a separate power shaft. Now you see, it's mentioned in the question that we have how many shafts? We have two shafts. One shaft is attached between the compressor and the turbine high pressure, and another shaft is attaching the low pressure turbine, which drive the power shaft. So a power shaft should be either running the WNet as what we want. Usually for a power plant, we need to run an electric generator. Okay. The isentropic efficiency of the compressor and the high pressure and low pressure turbine are 0.8, 0.85, and 0.83. Calculate the pressure and temperature of the gases entering the power turbine, the net power developed by the unit of kilogram per second mass flow rate, the work ratio, and the cycle efficiency of the unit. The maximum cycle temperature is 650 degrees C, and take the Cp value, the gamma value for air, and the Cp value and gamma value for the combustion gases. Neglect the mass of fuel. Of course, we also neglecting the delta Ke and also the delta Pe. So right now, we try to transfer all the data given to the schematic diagram or the arrangement of the what is given for this case. So what we have to do, of course, let us look. Let me clear everything. File, new, don't save. All right. So we have two shafts. We sketch the shaft. First shaft is going to drive our compressor. The second shaft is going to drive our WNet. Let's say in this case, I'm putting an electrical generator as our interest. So what we have right here, this is the compressor. So this is the turbine for high pressure. This is the turbine for low pressure. Right? Intake of the compressor should be state 1. which is equivalent, what is being taken right here is the P1 and T1. Okay, P1 and T1. And if we look in this case, 17 degrees C and 1.01 bar. So the T1 is 17 degrees C and the P1 is equivalent to 1.01 bar. What I'm sketching right now is I'm looking at the question, I'm trying to transfer the data. The first information that I have that I could use is to sketch how many shafts. Okay, how many shafts? So there is 2 shafts mentioned in the question. The high pressure turbine, a shaft attaching the compressor. Meaning what? Meaning the high pressure turbine is running the compressor. And we have the second shaft, which is the turbine low pressure, which run the W net, which is our generator in this case. Okay, next, we look what is being mentioned. The pressure ratio is 8. So this pressure ratio should be our overall pressure ratio, which is the maximum pressure ratio divided by the minimum pressure. The maximum pressure divided by the minimum pressure. So where do you think our minimum pressure? And where is our maximum pressure? Okay, so assuming that this is the output of the compressor, the only place that we have a compression process is in the compressor. Meaning that our P1 is our minimum pressure and our P2 is our maximum pressure. Okay? And again, the maximum pressure should be the inlet of the first turbine. And the minimum pressure should be the outlet of the last compressor. In this case, our last compressor is the turbine low pressure. But at this turbine high pressure and turbine low pressure, exhaust and inlet, we haven't put any numbering yet. So what we have right here is just for the compressor, which is P2 maximum, P1 minimum, and this is given as 8/1. This is 8/1. Okay? And then next we go, the compressor driven by the compressor is driven by the high pressure turbine. We have sketched that. And the low turbine drive a separate power shaft. So this power shaft, I have attached an electrical generator. Then we know that all the 3 devices, expansion and also the compression, everything has isentropic efficiency. And if we continue reading the question, calculate the pressure and temperature of the gases entering the power turbine. The net power developed by the unit per kg mass flow rate, the work ratio, the cycle efficiency of the unit. And then it's mentioned right here, the maximum cycle temperature is 650. So where is our maximum cycle temperature would be? What do you think? Where is our maximum cycle temperature would be?
At the high pressure turbine, sir.
Yes.
3.
Before entering the high pressure turbine. So if this is giving us the maximum temperature, you know that this is only 17 and the compression, after the compression is 2. Do you think that this compression process will give us up to 650 degrees C? can T2 reach 650 degrees C? What do you think? Let us calculate.
Not possible, sir. I think.
Not possible. But we could calculate what is our T2S. Let's say we take T2S. This is 2, right? And we know that the compressor has isentropic efficiency. So we could get what is our T2S first. What is T2S? The T2S equal to the T1 P2 divided by P1 power of gamma A minus 1 divided by gamma A. And if we look at the solution of this textbook, this type of compression, which is given us as the isentropic compression, will only give us 5 to 5. Okay, 5 to 5. And then next we get the T2. The T2 only will give us 8584. Okay, this is in Kelvin. The question tells us that the maximum is 650 in Celsius. Therefore, it must be a place whereby we increase the temperature of the T2 up to 650. And what we have learned right here, the only place that could increase this temperature is a combustion chamber. And this combustion chamber will lead the temperature as state 3. Okay, let's say this is state 3. And the temperature of T3 in this case is equal to 650 degrees C. Okay, guys, I need to explain this very carefully. Okay, very carefully, because a lot of students, they omit the combustion chamber. What they do, they don't draw the combustion chamber. Instead of a combustion chamber right here, they just continue to draw a straight line. And what they assume that the T2 is 650 going to the first turbine. Okay, which is wrong. That's why we need to see what is T2S and we need to see what is T2. If the T2S, especially the T2, if less than the maximum temperature, meaning that we must have some sort of device, which in this particular case, we need to put a combustion chamber, which representing the place whereby we input the energy. And also, you must understand, if you don't have the combustion chamber right here, where are you getting the energy to run the electrical generator? Because we know that first law of thermodynamics, energy in is equal to energy out. If you don't have input of enough energy, then how are you going to get this work? Because you know that in this case, the energy input should be enough to run the turbine high pressure and also should be enough to run the turbine low pressure, which will use to run the electrical generator. From the whole process, actually what we want, from the whole process here, actually what do we want? Where is our interest?
WN net, sir.
Yes, this W of this electrical generator. Why do we use the power plant? The power plant is basically a plant of converting heat to work. So you must have a place whereby you put in heat. And in this case, for the turbine side, for the turbine plant, the heat we input is always in the combustion chamber. Right? And then after entering the first turbine, which is high pressure turbine, there's nothing describing about before entering the temperature low pressure. Therefore, what is coming out from here, we are going to flow in to this turbine. And then it's going to be exhaust to the surrounding. Now we have already connected each component with the flow line. So if this is 1, this is 2, this is 3, this should be 4, and this should be 5. Okay? And remember, this temperature is given. This temperature is given. Okay. So now let us look. How do we solve this type of schematic diagram? How we solve the temperature? I'm only looking at the solving of the temperature. Okay. So this is how we solve the temperature of the temperature of this T2S. Okay. And then how do we solve the T2? We use the isentropic efficiency of the turbine high pressure, which is equal to T2S minus T1 divided by T2 minus T1. Now, I want to ask you, can you write this equation without looking at the TS diagram? Any response? I ask the same question again. Can you write this equation without looking at your TS diagram? Guys, macam mana? Boleh tak? Boleh tak? Tak boleh. Susah. Susah. Kita tak ada guide tau. Tak ada benda yang guide kita. In turbine plant, okay, gas turbine plant, we need both. We need the schematic diagram together with the TS diagram in order to solve for the temperature. Always. Okay, always. And to make sure that before you sketch the TS diagram, you must make sure that your schematic diagram is correct. How to make sure the schematic diagram is correct? Read the question and then you sketch. After that, once you completed the sketching, what you do, read the question again and make sure that the question, when you read, it reflects the schematic diagram. That only the way we can make sure that our schematic diagram is correct. If we read the question again, it does not reflect what we have drawn in the schematic diagram, then you have to redo it again until you get exactly what being said in the question, in the problem will reflect what is used, what has had been sketched. Okay? So in my case, I cannot solve the temperature without looking at the TS diagram. So meaning that after sketching your schematic diagram, I would advise you to sketch your TS diagram. So let us put this TS diagram. 1, 2s, 2, 3, 4s, 4, 5s, 5. Don't forget the arrow showing the direction of the process. Okay? So we have 3 isentropic efficiency. Now, can you see T1? We have solved T1. We have solved T2s. You see right here? Isentropic efficiency of compressor. Shorter line divided by longer line. Okay, shorter line divided by longer line. So this is our equation. Where is our shorter line? T2s minus T1 divided by longer line T2 minus T1. Then from here, T2 is being solved. Okay? Now, next, T3. What is T3? T3 is given. This is solved. This is solved. T3 is given. Right. What do you think that we are going to get next? We are going to get 4s or 4? What do you think? We are getting 4s or 4?
4s.
4s. How will we give, what do we use to get 4s? Now give me the equation. To what?
T3.
T3
P4 over P3.
P4 over P3
Gamma G minus 1 over gamma G.
Gamma gas.
gamma G minus 1 divided by gamma G. If we analyze each parameter, okay, we have T3. Do we have P4? Do we have P3? Guys? Jangan diam lah. I'm asking you question. Do we have P4?
No, sir.
Do we have P3?
Also no.
Yeah, we could get the P3. Okay, because we know that the P3, we could get the P3. Why? Because we know that the P3 is equal to P2, correct? P3 is equal to P2, correct? Betul tak?
Yes, sir.
Yes,
And
sir.
then we had the P2 over P1. Betul? Which is equal to 8n. And the P1 is given. The P1 is 1.01 bar is given. So in this case, you can get P2. No problem. Which is equal to P3. But the P4 is still our problem. Therefore, we cannot get T4S first. Okay? We cannot get the T4S first. So we need to get other relationship in order to solve either for T4 or T4S. So remember, pardon?
Continue, sir. Continue.
I'll continue, okay. I'm going to continue, inshallah. So remember, this T2, we have solved it. Okay, we already get the T2 right here, correct? So what are we going to do? We are going to use the relationship between the turbine high pressure work and the compressor work, whereby from here, from this shaft, we are getting the W12 equal to W34. You see? W12, what is W12? Is equal to W34 What is W12? W12 is CPA T2 minus T1 is equal to CPG T3 minus T4. This is the extra equation that we have. Now we look each parameter. CPA, of course, constant. You could get that, no problem, given in the question. We already solved the T2. We already solved the T1. T3 is given. So what we get from this equation?
T4.
T4. If this arrangement is at one shaft, as the first case, let's say the turbine high pressure, turbine high pressure, and turbine low pressure is attached with the same shaft. Can we use this formula?
No, sir.
No,
sir.
no, please, no, you cannot use. This formula only valid for this type of arrangement. Okay? Remember that. This formula, which is the W12 equal to W34, is only valid for this arrangement. If we have the one shaft connecting all the three devices or the four devices, which is the compressor, turbine high pressure, turbine low pressure, and electrical generator, you cannot use this formula. Because this is the formula of energy balance. The energy balance is what? The work needed by the compressor is equal to the work produced by the turbine. That is our energy balance equation. But for a one shaft case, you have your W net right there. The W net is equal to W turbine high pressure plus W turbine low pressure minus W compressor. You cannot easily cancel the W high pressure turbine with the compressor. We don't know. Okay, we don't know what is the value. But in this case, yes, all the work produced by the turbine high pressure is being used to run the compressor from state 1 to state 2. So this will lead us to what? Will lead us to T4. And again, after that, what do we use? We are going to use the isentropic efficiency of the turbine high pressure. Turbine high pressure. Okay, I need this diagram, and this is T3 minus T4 divided by T3 minus T4S. What do we get from here? This is given, it's given, it's given, and T4S we have solved right here. What do you get?
T4S.
T4S. Okay? And if we look back this question, this equation, what do you think that we get? Looking at that equation that we have written before this one, okay, that
P4, sir.
which cannot solve our problems now, that is 4S. But from this equation, what we can solve is P4 over P3. Okay? We solve the P4 over P3. Right? So, we look again. We have solved this. We have solved this 4S. Now, we need to solve next. What do you think we need to solve? 5 or 5S? Which one?
5S.
5S. Are you sure 5S? Okay, let us look. So how to get the 5S? T5S equal to T4, T4 or T4S? Here is T4 or T4S? See carefully, The beginning of expansion process in the turbine low pressure begin at 4, not 4S. There's no line at 4S. Okay? After 4S, there is no line continuing the process. The continuing process is just from 4 to 5 and 4 to 5S. So, meaning that this is T4, not T4S. So be careful on that. Always look at the actual condition, the actual temperature. So we are looking at the process of 4 to 5S. So this is the process from 4 to 5S. Okay? So can we solve this? You already get this, correct? So, sorry. So what we do, we need P5 over P4 in order to solve for 5S. So now, if you look, we have the overall pressure ratio, okay, overall pressure ratio, which is P2 over P1. And we also have the pressure ratio of 4 and 3. So this is the overall pressure ratio, P3 over P5. P3 is equal to P2, P5 equal to P1. So apart from P2 over P1 can be written as the overall pressure ratio, we can also write the P3 over P5 as our overall pressure ratio. So I need this guide. I need this CS diagram. Okay, I need this CS diagram in order to look the pressure ratio, the relationship between pressure ratio, which is the P3 over P4, P4 over P5, compared to the overall pressure ratio. So what I could write from this TS diagram, as far as the pressure ratio is concerned, I'm writing this is overall pressure ratio, and we know that a P2 is equal to P3, and P1 is equal to P5. This is equivalent the individual pressure ratio of the first turbine multiplied by the second pressure ratio, which is the turbine low pressure, P4 over P5. Do we know the P3 over P5? Yes, 8 over 1. This is given. 8 over 1. You see right here? We already obtained the P3 over P4 over P3, which represent the reciprocal of this. Okay, the reciprocal of this. In this question, in this equation, we need P3 over P4. So here is P4 over P3. So we already got the P3, P4 over P3. So from here, what do we have? We are left with P4 over P5 that we need in this equation. P5 over P4. So once we have solved this, once we solve for the P4 over P5, insert in this equation, then we get the T5S. Okay? So once we have solved the T5S, then we use the isentropic efficiency for turbine low pressure, which is equal to, see, I still need the TS diagram in order to put down the isentropic efficiency. Shorter line divided by the longer line. T4 minus T5 divided by T4 minus T5S. T4 minus T5, this is a T4 minus T5 divided by T4 minus T5S. So we have solved the T5S. The T5 also, sorry, in this case we are going to get the T5. The T4, we have solved the T4. And from here, we are getting the T5. Okay? So that's how we solve all the temperature with this type of schematic diagram of the plant. If you could remember just now, I said to you whether we are going to use this plant or the plant with one shaft, we are going to get the same TS diagram. Okay, we are going to get the same TS diagram. You see, this W12 equal to W34, where do we get it? We get it from the schematic diagram. Okay, that's why I told you just now, we need to make sure that our schematic diagram is correct. And then we sketch the TS diagram. So that is how you solve it. See, get your T2, isentropic efficiency, you get your T2. And then you see at the work output for the compressor, which is equal to the work output for the turbine. See, same value, same value. Then you use your isentropic efficiency to get your T. In this case, T4. Then we get the T4S. Once you get the T4S hilang lah. Okay, after solving the T4S, we are going to solve for the pressure ratio. So this is your pressure ratio. You see, this is the relationship between the pressure ratios. Then we get the P4 over P5 or P5 over P4. And lastly is to get the power output, which is equivalent to the power output of the low pressure turbine. Get the work ratio, get the heat supplied, and we get the thermal efficiency. Okay? So you try using the formula that I put, and you look, make sure that you get the correct answer. Now, what I'm going to do is to look at one question in the problem section. This is our problem. The first problem, 9.1, I think is very simple one, but it's incorporate with the mechanical efficiency. Okay, let us have a run through the question first. A gas turbine has overall pressure ratio 5. Maximum cycle temperature of 550. The turbine drives the compressor and electric generator. You see, the turbine drive the compressor and electric generator. The mechanical efficiency of the drive being 97%, the ambient temperature is 20 degree, the enters the compressor rate is 15, we have isentropic efficiency for the compressor and turbine, and then neglecting the kinetic energy, potential energy, pressure losses, and the mass of fuel, calculate the power output. So, what do we do? Ask ourselves. Okay, ask ourselves, how many turbine How many compressor? Okay, that should be the first question. If we look in detail the question, we can see that there's only one compressor and one turbine. And being said that the turbine is going to drive the compressor and also an electric generator. So the whole component of these three, which is the compressor, the turbine, and electrical generator, should be drawn as in one shaft. And we have the maximum temperature of 550. And again, the maximum temperature should be the temperature at the inlet of the first turbine. Because we only have one turbine, then it's going to that turbine. And how to get the increment or the high temperature before entering the turbine? Then we must have a combustion chamber. A combustion chamber. So if I could conclude this type of schematic diagram for 9.1, so what I have right here, I should draw a compressor, having a shaft, drive by turbine, and this same turbine will drive an electrical generator. This is our electrical generator. And as we know that we have a maximum temperature, so this is our combustion chamber. Okay? So to complete, we put on the flow line. Exhaust, compressor, turbine. 1, 2, 3, 4. Okay? And then the mechanical efficiency of drive being 97%. What do you think you should put this statement of mechanical efficiency? The turbine drive the compressor, an electrical generator, and the mechanical efficiency of the drive being 97%. What do you think? Where do we put the mechanical efficiency? Where, guys?
Between compressor and turbine, sir.
How about the turbine and the electrical generator? It's also driving the electrical generator.
Both, sir?
You know, we have to take care of both. How to take care of both? All right. So now we might have the mechanical efficiency of this side, and we might have the mechanical efficiency of this side. Okay. So if we could write the work of the turbine and the work for the both of the driven by the turbine, what we could write here, the W turbine is equal to the W for the compressor plus the W, in this case, the W for the net, which is the electrical generator. So this is W net. Okay. Remember that our efficiency. What is the efficiency or the definition of our efficiency? Desired output divided by required input. Who is the required input?
Compressor.
Which device? Desired input. Sorry, required input. Sorry, required input. The required input. Who input the energy? Who gave the work?
Turbine.
Turbine, right? So
Yeah.
meaning that this should be our turbine side, correct? That is our required input. So what is our desired output? The desired output is basically based on the work of the compressor and work for the W net. So meaning that this is our desired output. We must get enough work from the turbine to run the compressor and also the W net. So what we have right here? This is taking care of both of the mechanical efficiency. Right? So what is W turbine? The W turbine is equal to the W compressor plus the W net divided by the mechanical efficiency. Or you can rewrite that as what? The mechanical efficiency multiplied by the turbine is equal to the W compressor plus the W for net. It's up to you. What do you want to get first? But along the way, you must put the mechanical efficiency. So how to put the mechanical efficiency? Always look at the definition of mechanical efficiency. Look the definition of efficiency. So when we look the definition of efficiency, this is our definition. Okay, this is our definition of the efficiency. The desired output, which is both work of the compressor and also the W net, divided by the required input, which is the work for the compressor. So this is what you have, and this is where you put your mechanical efficiency. So basically, the mechanical efficiency you put in whereby when you solve for the temperature. Okay? So that is how you look at it. And also, after this, you sketch DTS diagram. Okay. Now, let's try to discuss the 9.2. A marine gas turbine unit, a high pressure stage turbine drives the compressor, and the low stage turbine drive the propeller to a suitable gearing. So in our case, maybe we can change the propeller to a electrical generator, because our interest in thermodynamic is always the power output from the plant, which we are going to use to run a generator that is being used right now. Okay, the thermal power plant, which is one of them is the gas turbine plant, is used to run the electrical generator. So maybe we can change this to electrical generator to use propeller. Given the overall pressure, and then we have given the mass flow rate, and the maximum temperature is 650. Given the air intake condition 1.01 bar, 35, the isentropic efficiency of compressor, high pressure turbine, low pressure turbine are 0.88385, and given the mechanical efficiency for both shafts, now it's given the both shaft is 98%. Okay, neglecting kinetic energy pressure loss, calculate the pressure between turbine stage. Okay. Now, how many compressor? For sure, we have two turbine. High pressure turbine, low pressure turbine. The mechanical efficiency of both shaft, you see, it being said that high stage turbine drive the compressor and low stage is driving the low stage turbine is driving the propeller, which we assume that electrical generator. So we have two shafts. Okay, two shafts. High pressure connecting to the compressor, low pressure connecting to the electrical generator. Now, in the case of, we have isentropic efficiency for 3 devices, and then for the 2 shaft, we have mechanical efficiency. So try to sketch this schematic diagram, and then convert all the processes from the schematic diagram using the suitable numbering, sketch the TS diagram. Okay, guys?
All right, sir.
So I think that's it for today. Did I share my screen? Guys?
Yes,
Share,
sir.
sir, share.
Yes, sir. Yes, sir.
Yes,
Oh,
sir.
terkejut saya. Ingat saya tak share. Okay. So let me take your attendance first before we leave for today. Okay, there is your link for our attendance for today. So